Hello everyone. Welcome to this problem solving session. We will get started now. So I hope am I audible? So is if there is some doubt from previous session, then I will pause for some time, and otherwise we will start the session with today's session. So is there any doubt from the previous session? You can ask. I will pause for some time, and then we will start this session. So yeah, the content for this week was mainly about resonators and filters. So resonator also you can count as a filter. So basically, uh, so the content for this week. So this is the week summary. So the content for this week was resonators and a narrowband filter. Just wait. I think. Yeah. So the content for this week was resonators and narrowband filters. Uh, and then basically like the uh, uh, different filter design. So once you know which filter you want to use, so there are different kind of technique. So like this filter design technique, and like there are different kind of techniques are there. Image impedance method, and insertion loss method, and then basically like once you design the filter with the lumped parameters, then basically how you can convert those parameters into the distributed capacitance, and in terms of your shorted or open circuited lines. So basically that you can use as a resonator, and that basically that basically is the this week's summary. So let me quickly summarize the content a bit. So so any resonator, let's say let's say you are driving this circuit, and there are resistance and capacitance, inductance are there in this. So basically, what will happen? Like let's say you so what let's say in this circuit. So I am just explaining just by basic LC oscillation circuit. So let's say you fed energy to this circuit, and then basically here is the switch. So let's say here is one switch. So this is one switch, and here is one switch. So you excite this resonator by closing this switch, and this switch is open. And then now after like putting the energy into this LC circuit, basically you just open this switch. So when you will close this switch, so there will be energy stored in the capacitor. So in the capacitor, the electrical energy stored is half of q square by c, uh, uh, or half of CV square, right? Where V is the voltage across the, like now after excitation, this is the voltage across the capacitor, and this is, let's say, capacitor, and this is inductor. Similarly, the magnetic energy stored in the inductor Wm will be equals to half of L times I square. So now this I is basically the current in this inductor. So this is I of this is the current in the inductor. So now at the resonance, basically this energy. So once you close this switch, the energy will keep on passing into this and this, keep on oscillating between these two circuit element if you try to solve. So this basically work as a LC oscillator, and if you have like the perfect capacitor, perfect inductor, then it will oscillate for infinite time. If you there is no loss in that system. Obviously, in the practical devices, there are losses which in this simplest scheme it will after some time it will those oscillation will die out, but you can but in the ideal case you can consider this as a oscillator. So that basically can work as a oscillator, and you can like you c- yeah, yeah. Oh, okay, just wait. Just, uh, just so now is it clear? Now is it clear? Can you please confirm, is it clear? Hello, hello. Yeah, Anand, is it clear now, or is it same like the hello, hello? Is it clear? Yeah, is it clear now? Okay, so this is okay na right now. Okay, fine. I think like let's just get started. So yeah, so okay, so yeah, so that basically to find this for simple this LC oscillation circuit. So basically you equate the uh, electric energy. So the electric energy will be equals to the magnetically stored energy at the resonance. So basically, if you equate this equation, and basically like you can write the current in terms of circuit element. So basically, uh, you can write in the uh, uh, so in the in case of uh, capacitor, basically your voltage across capacitor is basically is you can write as a basically you can write as a q equals to cv. When q you can write as di by dt equals to cv, and the voltage across the capacitor you can write as V across the capacitor will be equal to 1 by C. di over dt. So, and if you are considering uh, uh, this oscillation with omega frequency, so this the voltage will be varying as a omega. So that basically that voltage you can write in terms of AC voltage actually. So that you can write just as the voltage you can write as V equals to dV by dt. You can write as j omega by c times. So this so you can write this instead of like the total timing equation, you can write in terms of uh, in terms of uh, in terms of sinusoidal oscillating voltage. So similarly, like you can write this in terms of current basically. Okay. 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 Just wait. I think let. Okay. Just wait. So I don't know why this today is so bad. So now is it clear? Hello. Hello. Is it clear now? Hello. Is it clear now? Am I audible? Is it clear now? Hello. Hello. Yeah, just wait. I think I am not able to hear your voice. So let me just. Can you speak and just let me know if it is clear now? Okay. Okay. Just yeah. Now also right. Okay. Fine. Okay. So I was explaining. So basically, you can write. So you can write. So, in terms of current and those equations, in terms of sinusoidal signal, you can write the this equation, and if you equate the electric and magnetic stored energy, then basically you can derive the expression for resonance frequency. You will find that that expression, if you equate electric and magnetic energies, you will reach out at that like omega naught square is equals to omega naught square is equals to 1 by LC. So basically, how you will get it? This you can write V in terms of I, and then basically you just equate the equation, and then rearranging the term, you will give you this. So let me just define. So basically, you can write. Let's say you have the sinusoidal current I of t is basically I naught sine of omega t. So then basically when you take the derivative, so it will become I of t. So di by dt will become it will become uh, this will become I of omega. You can write as like omega times. You can take di by dt. If you take, then it will become omega times I of t. And then basically you can write in this. So basically now you can write in electric energy. So this will become omega squared times c times I of t square equals to half of that half term will get cancelled. So this is half of half times times L times I of t square. So now if you take a side term to left side, then the only term will remain. So the I of t will be common. This will become omega square c minus L equals to 0 here, or times I of t equals to 0. So this term is not 0. So only the first term needs to be 0 to satisfy this equation. So then omega square c will be equals to L, and basically omega equals to just wait. No, this is 1 by c. 1 by c is there. So then basically you can uh, no, this will be 1 by L. So this finally you will get omega square equals to 1 by LC, and if you take the square root, then you will find out that the resonance frequency is LC, square root of LC. So this is the resonance frequency for uh, simple LC oscillators. So basically like this you can any transmission line. The impedance of any the transmission line. So Zn is given as this formula Z naught. I think ZL plus J times Z naught tan beta L upon Z naught plus J times ZL tan beta L. So if you vary the length of line, so basically you can tune the impedance of any line. So if you take, let's say uh, some open or short circuit line, then basically you can write the impedance either at Z in equals to J times Z naught tan beta L, or Z in is will be equals to 1 by J times Z naught tan beta. So this kind of, like, you can write for a shorted line this. And so as tan beta L will depending on the uh, depending on the line length, basically tan beta L can be positive or negative. So when it is positive, then basically your impedance is behave like inductive. So you can choose the length wisely, so that you can realize the those capacitance and inductance just by just by just by just by varying the length of line. Also like there are different kind of resonators are possible. So just wait. Different kind of resonators are possible, which you can realize by uh, different kind of method, which is like this air gap. If you like between two transmission line, if you assign an air gap between these two lines, so this air gap basically behaves as a capacitor. So that basically and this line, whether it is open circuit and short circuit, depending on you can write as a capacitance, or inductive kind of models. And also there is a loss in the line, so that is counted as a as a as a as a resistance in the. So you can model any network as a series or parallel resistance, and that basically, let's say if your network is in series, so this you can write is this RLC. This is R, this is C, this is L, and you can write as a impedance of this network as Z in is if you look at this from here, it will be equals to R plus 1 by J omega C plus J omega L. So this is the impedance of this line, and basically like you can for resonance, actually the energy stored in this network will be maximum, and you can find the uh, 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 in the like the this energy stored in the capacitive and inductive element will be same. And basically at that it will this network will become purely resistive, and that you can use for calculating the uh, the uh, for calculating the resonance frequency, you can use this condition. Also if you sweep the frequency of this source, and basically then your power if you are driving this network to drive some load, so basically your power will vary depending on your let's say this is L and this is R, which is the load you want to drive. Let's say this will constitute your resistive network, and let's say this is L. And then basically your like this will behave as a RLC circuit. So basically like you can calculate how much power can be delivered with the this and basically you can calculate the response with respect to the frequency. So you can so the as you plot with the frequency versus voltage or current, and then basically like the voltage or power across this register, and basically if you plot with this omega naught, which is resonance frequency, so this inductive and capacitive element will cancel out. This will be equals to 0, and basically your impedance will become only reactive, and basically then your power transfer to the load, and those will be get maximum. So at this you will have maximum power, which will be equals to the load delivery, and basically you can calculate the quality factors. This line width of this resonance basically so line width will give you the resonance. So if you calculate the line width basically, and these are this if it's say let's say this is the uh, P naught power, the maximum power, and this is the 50% power, half P naught point, and basically the frequency corresponding to this which is omega L and omega H, you can calculate the bandwidth. So basically and with and also like the main feature of this resonance is basically the quality factor, so which is equals to omega naught divided by the delta. So basically this is that basically you can call as a fractional bandwidth, or so so no, this 1 by q, basically 1 by q is delta omega by omega naught, and this is known as the fractional bandwidth. So this you can calculate for a series resistive circuit. You can calculate for this quality factor. So for the series resistive circuit, the quality factor comes as omega naught L by R. Similarly, for parallel shunt resistance, same like you can for shunt resistance you can connect this element in parallel, So you can collect this element in parallel. So basically, so this is let's say resistance RLC, and this is the source, and you can here you define the admittance. So admittance will be equals to 1 by R plus j omega c plus 1 by j omega n. The resonance condition will be same, and if you calculate the quality factor for this, then it will become omega naught times RC. So this is the quality factor for parallel RC circuit, and this is the main lumped element modeling. So if you have any doubt up to now, हाँ 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 या हम्म हाँ रेजोनेंस हाँ 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 so basically so basically the idea to introduce like this is not related to any kind. I just want to explain the resonance too. Just okay. Yeah. So yeah. So this like the summary is basically like different yeah. So different like you can we can discuss. So you have any specific doubt related to that? Because that I don't want to repeat whole content, but any specific doubt I can clear. हाँ 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 या हम्म हम्म हाँ so basically yeah hmm. So basically, so yeah, why we are discussing? So actually, your resonators are basically the perfect example of narrowband filter. So this comes in the narrowband filter. So if you have, let's say, designed the resonators, then basically you have designed the narrowband filter actually. We will design with the micro strip lines only. Yeah. We can discuss. So basically, like there are different kind of filters are there. So let's say this kind like that you can like different kind of topology you can explore. So basically, uh, uh, those are basically uh, like different. Just wait. Let me just open my notes. Yeah. So basically, this different kind of band stop and this different kind of filters you can design based on the parallel microstrip lines. So these type of filters are band pass filter and band stop filter. So band pass and you can realize you can like the this different so mainly these two types of filter you can design by different topology. So basically like you can take a series lines. If you like if you connect a series line resonator with just wait uh, yeah so if you connect if you connect a series resonator, let's say like this let's say you have a open or short circuit line, this will behave as a resonator actually. So now if you connect this with the series or shunt line, you can you can you can have you can have different kind of filter. So you basically, this line, let's say this is lambda by 2, or this section line, and you created an air gap. That air gap basically capacitively couple these two lines, and basically that, and if you add certain component in, like you can add in parallel or shunt. So let's say this is your line, and if you and if you add a section line in shunt, so this is the series combination and this is the shunt combination. So if you add a line in the shunt, then basically the uh, so basically different kind of topologies are there. You can realize the resonator by series combination, series line, uh, and also with the shunt line you can realize. So if you combine a series line with a series resistor, and also if you combine shunt line with shunt resistor, then this is basically behave as a band pass filter. And similarly, in other way, if you combine series line with the series line resonator in shunt with the with the other line, then also the shunt line with the series, then it will behave as a band stop filter. So these kind of this kind of line combination you can you can realize to to realize different kind of filters, and basically that you can basically use for different kind of different kind of topologies you can have. So basically huh, huh. Suppose suppose you want to like this open circuit, like let's say you want to define a define let's say you want you want band reject filter. So band reject filter, so you need to take series resonator with the with the with the with the with the with the shunt line. So what is the problem in that? Basically, basically you in certain conditions you can't because that open circuited line is not correct in that sense. So basically that topology is not good. So if you use other topology, then it may have a better better characteristics in terms of or it will have a better performance compared to the other topology if you use. Okay, so let's say so basically so let me just yeah. So uh-huh. Okay. So basically this the like the shunt, let's say you want to let's say this is this is a transmission line. So like it's difficult to for open circuited lines. Let's say this is open circuited line, and you want to connect a shunt resistor in series. So that topology is difficult to realize actually. So that may not have better characteristics. Particular example I can give, I don't know, I could not remember the particular example of this. Uh, I don't have example in mind particular. So yeah, hello. So like this different kind of this, let's say you want to you can design like this also, like the series combination like this. Uh, and this, let's say this is z naught is the input line and z naught is the output line, and you this line is basically your this, so uh, this is lambda by 2, and basically you can model this line as, so if you are fading with from this direction, so you can write the model as some loss corresponding to that z naught, plus because this air gap is there, and also this because of this, and this is lossless line, so there will be no resistance, and there is a load, so you can write as a z naught. So this z naught and z naught, so this you see like this is capacitor, this is capacitor. If c, both c are same, then your equivalent circuit is basically your C times Z naught. So basically, this will behave as a as a low pass circuit. It will start behaving. Huh? So this the total. So the V out. V out by V in will be equals to Z naught by 1 plus Z naught plus 1 plus J omega C, and that basically you can write as a this you can write as a uh, z naught you can take common 1 plus 1 by j times z naught omega c, and for this you can see like the as you have very high frequency, then that v naught for high frequency it will that v naught will be equals to v1. So basically, this will pass. So this will behave like a short circuit, and all that power will be transferred to the load. And at the low frequency, it will that capacitor will block, and basically you will have the response like this. So you can have the response like this. So it will behave like a like a high pass filter, right? Similarly, if you can design the if you can design the element such that this your load line is the capacitive final, and your this is z naught and this is capacitor line. So to create the capacitance, basically you need to create a shunt. So to realize the low pass, so basically you need this kind of circuit. So for that you need to create a lambda by 2 line in the shunt you need to put. So that's why you need so this is port 1 and port 2. So if you combine these both two mechanism, so basically one will behave a low pass and other will behave as a high pass, and then if you cascade these two lines, then basically your filter response will become band pass. So is that clear? Yeah, what is the doubt? Hmm. Huh. Uh-huh. Huh. Yeah, so basically, like this kind, huh, as a capacitor, yeah. Hmm. Yeah, so that is connecting your port one to port two. You just add it. So basically, you are taking output at this node, all right? So this line is just Z naught impedance line. So this is Z naught impedance line, and you just want to create a shunt in there. And you can realize in this, like if you connect a next line, then the here it will be Z naught. So basically you can design a T, this will behave like T kind of circuit actually. So basically, like this, at the output port there will be load, na. So the if the impedance matching should be there, there should be a load actually. So that basically, so that load you can model with the one resistor actually. Yeah, right. So that's how these topologies are important. So depending on like I just uh, so be, so basic. So this is you can like lambda by 2 length. So it is behave like this will, if this line is open circuit, that here it can behave as a short circuit also. Like you can make a short circuit line also with this lambda by 2, depending on lambda by 2 or lambda by 4. You can create a short circuit or open circuit line. So if you create this as a short circuit line, so this will be shorted, and the air gap will be grounded to the source, right? So this can be either short circuit or an open circuit line. So that basically, like this line you can design whether you want this node to, whether you want to connect in shunt on series. You can design basically based on those, like you want short circuit or open circuit line, yeah. But the floating open circuited stuff, like those are like difficult. So the line is basically shunt, like the short circuit is short circuit is better in shunt, and open circuit is better in series actually. If you use other way, then so basically you can tune the length, na. So basically see like the this z naught, z in basically of any line is z naught times z naught plus I think j times zl, 10 of beta l, and one ZL plus J times Z naught 10 beta L. And if you do open circuited, then basically also you can calculate the impedance based on like the for short and open circuited, you can calculate what is the impedance. So this will have finite impedance if you tune the length actually, right? Yeah. So basically length you need to tune. So basically length, you can use like the simple like that quarter wave transformer. So basically if you have so that let's say you have so let's say uh, this was the in the first lecture, let's say you have ZL connected to this Z node line. So what will be the input impedance? So if you use lambda by 4 line, it will be Z naught square by ZL, right? So if you put ZL equals to infinite, then this will behave like a short circuit line, right? Like this open circuit line will behave like short. Similarly, other way around situation also you can create. So if you uh, uh, that is Z dot zero square by ZL. Mm-hmm. Hmm. So basically ZL, if you can have ZL open or you can have ZL short. So let's say ZL is open. So that the open means infinite impedance. So basically that net impedance will be will be equals to 0. So Zn will be equals to 0. So basically, if you use lambda, uh, hmm, yeah, so Zl, hmm, yeah, so hmm, yeah, so this line will start behaving like a short circuit actually, as a short circuit. Yeah, this line which I marked. Yeah, this one, right? uh, Shorted line. And other way around, if ZL is equals to 0, then Zn will be infinite. Then it will behave like open circuited line. And if you if you can this I one case, the total impedance, if you are considering like the open circuited and short circuited line, let's say any finite length L, so this the impedance will be J times Z naught 10 beta L, and other case it will be 1 by j times z naught 10 beta n. I think one is for short circuit, other is for open circuit. So basically what will happen, like n length if you tune, then see like the zn can be like if it is a form of j times omega l kind of function, then you basically behave like inductors. And if it's like minus like 1 minus j by omega c kind of function, then it will behave like a capacitor. So based on the line length, you can just calculate even the short circuit line. You can like work as a capacitor or inductor based on the length you tune actually. So yeah, so you need to decide which topology is suitable. So like the this is normal convention, like the if the short circuited line is better in shunt and open circuited line is better in series. Actually. So actually because like this connecting two transmission line and then connecting the series line in between is very difficult. It will not be that good actually. Matching those is very difficult. Yeah, so basically, if you are using short circuited line, then better you use in shunt, and if you are using open circuit line, you use in series actually. So yeah, so like bit complicated, but like just you give a thought, and then like if you have any doubt further, then just let me know. Uh, okay, huh. So there are in the like the site also there are some solved examples are there. You try solving maybe those, then I think we can discuss. You can ask in the next class if you have any doubt. Yeah. Yeah. So I think let's just move to the problem solving session. I think we are 1 hour. Yeah. So we have 1 hour. So so uh, the problem. So let's move to the problem solving session. So the resonator at the resonance store actually. So that's what I explained initially, that it is stored the equal amount of electric and magnetic energy. So basically, at the resonance, you electro energy will be equals to the magnetic energy, right? So that is just straightforward. So the other options are unequal amount of electric and magnetic energy, depends on the circuit configuration. No, this is wrong. This is wrong. None of the above is all wrong. So this was the so this resonance is a narrowband phenomena actually, because see, like if you consider the LC equivalent, the resonance condition occur for like only one combination of L and C. So the resonance free, or like let's say you have some circuit, so only very near that narrow band of frequency it will pass, or it will have like this kind of response. So very so this is a narrow band response. If you have depending on the on your like quality factors, basically this is the narrow band. The wideband response is look like this actually, like this flat. So if you can, so those are wideband, but typically the resonance is narrowband phenomenon. Only that loss in your circuit make it wider. So however more loss you have, it will have broader resonance or worse quality factor. The lesser, so the if you consider the series resistance, so basically quality factor is omega L by R. So if you reduce R, so basically your quality factor will keep on increasing actually. For if you consider R equals to 0, then basically it's like in quality factor is infinite and you will have infinite oscillation of this. That is the example of uh, your typical LC circuit actually. So this is the narrowband resonance is very narrowband phenomenon. So this which option is is that clear that question? Okay. So let's just move to next problem. So which option is correct? So series resonator has a minimum impedance at the resonance frequency. So series resonator you can write as a so you can write like this, or let's just write like this. So we can write like just like this. So this is your series resonator RCL. You can write the Z in as uh, R plus J times omega L minus 1 by omega C. So at the resonance frequency, basically, this the impedance will be minimum. So basically, this if you calculate the magnitude of Z in mod, then it will be equals to R square plus uh, omega L minus omega 1 by omega C whole square. So at the resonance, this term is zero. So you will have the minimum resistance. Similarly, like uh, the in case of shunt resistor, actually shunt topology. So basically, you have inductors like this. So this you can write as a admittance as 1 by R plus 1 by 1 by R plus uh, uh, J times omega C minus omega L, and at the resonance this will be 0. So this your admittance will be minimum and your impedance will be maximum. So the admittance will be maximum, sorry, admittance will be maximum and impedance will be minimum. And impedance is basically Z in will be equals to 1 by this inverse of this admittance. So that you can basically write as a 1 by R square plus uh, omega L minus omega 1 by omega C whole square, and this is square root. So that basically to answer this question. So Resonator has a minimum impedance at the resonance frequency. Uh, Shunt resonator has a maximum impedance at the resonance frequency. So the both answer are correct. So the correct option is both the. Okay. So is that clear? Yeah, yeah. This is what this is. So then basically the next problem talks about the quality factor. So the quality factor for series resonator is given by omega L by R, and it is for shunt resonator it's given as omega naught RC. So for series resonator increase as resistance increase for series resonator, if this denominator increase, that quality factor will get decreased. So this first option is wrong. Increase as a resistance increase for shunt resonator. If you increase this resistance, then quality factor will get increased. So the second option is correct. Decrease as the resistance increase for shunt resistor. This is wrong because like the third option is correct. Decrease as the series resistance decrease for series resistor. If you decrease this, then this term you will get increase actually. So the correct option is this one, second one. Is that clear, right? This one. Yeah. Hmm. Yeah. Hmm. This is no, this is for two different. This is for shunt RL shunt type, and this is for series. So uh, yeah, yeah. Series capacitor. Hmm. No, no, series inductance shunt capacitor. Yeah. Hmm. So this basically like you can drive for this is the basically relate. Yeah. Hmm. So yeah. So uh, so basically, you can write. So basically, if you write Z in versus omega for series and shunt, so you can write as a for a series it will be like this. So at omega naught it will equals to R, and for a shunt it is like just like that this r is maximum, so it will be here we have like this. So this is z in for shunt, and this is z in for series. I think I am correct. Yeah. Hmm. So that basically you can write and you can define the quality vector. So because for series and shunt like the impedance profile is different, so that's why your quality factor equations are different. So one case it is maximum at resonance, other case it is minimum at resonance. Okay, so uh, so uh, yeah, so that basically choose the correct option. So a short circuited lambda by 2 line can act as a series resonator. So basically, uh, so you can basically like the short circuited line. So if you let's say this is the our generalized equations is we can write as a generalized impedance equation. We can write as for short circuit line. We can write as a input impedance as so just wait. For short circuit line Z naught, Zn, you can write as J times Z naught 10 beta L, 10 beta L. So now for this, uh, so uh, so basically, like you can like if you let's say this is your fading line. So let's say you if this is your fading line which is has Z naught impedance, and you have connected a lambda by 2 line, lambda by 2 short circuit line. This next is short. Uh, right. So that let's just calculate what is the input impedance at the this. So basically that will be equals to this, and you can calculate the impedance of this line Z naught times 10 of beta L. Basically that, and basically now you can calculate beta is 2 pi by lambda, and your length is lambda by 2. So this will get cancelled and this will get, and 10 of pi is minus 1. So it is minus j times z naught. So it is behaving like a capacitance. Uh, they are like you can write as a this z naught resistance plus air gap capacitance plus this load capacitance, that you can write, and basically you can calculate this uh, this just wait no this is a lossless line actually. So the it has a characteristic impedance, but at input there is nothing appearing actually, because now it's behaving like inductance, right? You, because you short circuited it, that's why this properties got changed. uh, so uh, so this like because you change like like you short circuited this line, na? So that's why your input impedance will is behaving like that, right? So now basically this is behaving like a capacitance. So it's basically like that you can you can like this can act as like uh, if you short circuit line, and if you connect in the series, basically that it can behave as a line. And also you can calculate for open circuited line. So the open circuited line, the input impedance is z is basically 1 by j times z naught 10 beta l. Then it will become 1 by j times z naught. 10 beta L will become 10 times beta is 2 pi by lambda times lambda by 4. And this lambda you can cancel. So basically, then basically you can write this as this will become pi by 2, and this will become like a short. So open circuited line line will just wait. Open circuited lambda by 2 line act as a shunt resonator. Yeah, just yeah. So basically, like this, you can shunt resonator if you well. So basically, like now this will behave this will behave like just I think short circuit line. Mm. So let me just I have a confusion. So the your total input impedance is basically Z times Z naught, ZL plus J times Z naught, 10 beta L divided by Z naught plus J times ZL, 10 beta L. So for open circuited line, ZL is infinite. So basically, this 10 beta L term is smaller compared to your first term. So basically, it will become Z naught ZL by uh, J times Z naught 10 beta L, ZL 10 beta L, and this will become okay. Yeah. So basically, the open circuit line, the impedance will be basically J times Z naught 10 beta L, and for short circuit line it will become J times Z naught 10 beta L. So when like this, if you can take lambda by 2 line basically, then basically it will start behaving like this beta L is pi by 4, and then basically like it will behave like the it will behave like the short circuited line actually. So like this will time will get infinite, and your input impedance will behave like a short circuit line. So so basically like if you connect the open circuit and lambda by 4 line, that means you are connecting in shunt actually. So because that it's behaving like a short line. So the correct answer will be I think a short circuited line. Correct answer is uh, I think correct answer is first one. So this like other one will just behave like a shorted line actually. So it won't behave like any reactive element. So the correct answer is first one only. So only the lambda by 2 line behave like a resonator. Lambda by 4 line won't become the resonator. It just basically it will just become open or short only. It won't behave like a reactive element. Is that clear? Hello. Okay, fine. Okay, so let's just move to next problem. So the unloaded quality factor for shunt resonator is so like this unloaded quality factor for a shunt. Loaded quality factor is basically like let's say you have a resonator. So let's say you have uh, you have let's say this resonator. So you can equivalently you can write like this. So this is a resonator, right? So now if you connect a load and any load which is other, then total resistance will get a change actually. So this is let's say this has a R L C, and this is R L. So for to calculate the loaded quality factor, you need to consider the total resistance actually. For like for shunt resistor, shunt topology for loaded quality factor L will be equals to omega naught R plus RL times C. And for series, loaded will be omega naught uh, L by R plus or R total you can write. So that, but here it's right unloaded quality factor. That means you are not connecting this line. So basically, what is the unloaded quality factor for shunt resonator? It is basically equals to omega naught times RC, as you can drive also. So this is the uh, correct. Uh, the uh, so now basically now you can this is the so is there any doubt related to this? uh Which one? Yeah. E. This one like this. If you don't connect any load actually, so basically any load you are trying to like let's say you what is the meaning of loading an resonator? Suppose you design a resonator, you want to extract some energy out of this, or you want to, let's say, excite also a resonator, that also causes this loading. So basically the loading means you are connecting every resistor across the resonator. So basically that will there will be a drop in the quality factor if you load the resonator. But here only unloaded quality factors are there. So that means there is no load connected in this this quality factor calculation. Is that clear? Yeah. Ha. Hmm. Yeah. So basically you don't. Ha. R times C. Yeah. So this is for loaded case. This is for loaded case. So this is for loaded case. Yeah. R plus RL times C. Yeah. Times C. You just basically you add this resistance in the parallel. So basically just they will just get added in parallel. Yeah. In place of R you just made R plus RL. Yeah. Uh, yeah. Just yeah that R will. No, load resistance will not be there, but internal characteristic impedance or that R will be there, right? Anyway, yeah, that is. So whatever the we drive earlier, it was a unloaded quality vector. Okay. So 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 uh, let's just move to next problem. So basically choose the correct option. Bimonomial response can be used if the filter design require sharpest cutoff. Chebyshev response should satisfy the requirement of the minimum insertion loss in the filter design. So basically, like the Chebyshev, basically what you do, you connect multiple stages actually. So like the similarly like the Chebyshev like impedance transformer design problem, it is similar to basically your response will become n times actually. So that so basically like the insertion loss. So basically your you can write insertion loss in the filter as so L insertion loss is basically 1 by S21 mod square. And for this the for this filter you can write omega by omega c. If you are n stages, then it will become 2 times n. So basically, binomial. The to have the sharpest cutoff. So basically, if you keep increasing n, so basically your cutoff frequency will become like this. So like this, then like this, it will become sharp and sharp as you keep increasing the n. So if you increase n, the filter response will become more sharper and sharp. So for better sharpest cutoff, Chebyshev response you should use. So this is the Chebyshev. Basically, you connect a multiple stage, and then like that you that similar to like multi-section Chebyshev transformer. It's just similar. So the Chebyshev response should specify the requirement of the minimum insertion loss. No, the insertion loss will become higher and higher. So this is wrong. This is wrong. a better phase response will be obtained using Chebyshev response. No, no. The cutoff or sharpness will get increased, but if you plot the phase, it will have additional phase lag actually. The lag will be more and more actually. It will be slow. So the correct option is for the sharpest cutoff, Chebyshev response can be used. So this basically multi-section if you use, then basically you can just increase the response of the filter. So yeah, so right. So the for this problem, uh, this is related to image impedance. That basically you can write as so the image impedance is given by Z. So the image impedance. What is the image impedance? So let's say if you if you connect load if you connect a load a certain impedance, and if that is same is appearing at the input, that is known as the image impedance. So that for a network is given by Zi1 at the first port is given by you can write in terms of ABCD parameters. ABCD is basically equals to Z11 divided by Y11. Similarly, Zi2 is BD by AC, and it will be equals to Z22 by Y22. So basically you need to calculate Z22, Z11, Y11, uh, Y22. So to calculate the Z11, so basically now to calculate the Z11, you need to open this port. Means if you open this port, then this other will be ineffective. Only your impedance will be J times omega L by 2 plus 1 by J times omega C. So this is your impedance. This is Z11, and similarly you can calculate Y11. So how you calculate Y11? So the it is the input admittance provided that you short circuited the output. So to calculate the Y11, it will be like this. So this the capacitance, and when you short circuited this output, then this will become in parallel. So this will become J times omega L by 2. This will J times J times omega L by 2, and this is 1 by J times omega C. And so basically you can calculate the equivalent admittance, and that will be equals to your by admittance. Similarly, you can write the Z22 and Y22 you can calculate, and basically this all omega is given, L is given, C is given, so all is given. The image impedance, once you calculate Z11, Y11, you can calculate the image impedance, right? So this will the if you plug in all the values, then this will come around 22, I think. So is that clear? Hmm. The image impedance. So it just you just Z11, you just put the 1 gigahertz is the frequency. L is given as zero point 0.5 nanohenry. Omega is given as one frequency. C is given as 1 picofarad. So all the values, then you can calculate Z11. You can take mod of this. Then similarly you can calculate the equivalent of this. This is Y. So you can calculate Y also. Once you take the mod, then J will also go. Or J will become common, because these are all RLC component only. Na? J will always come common. Once you will take the ratio, then that will get cancelled out. Right? Uh, Uh, Under root like so Z so this is the image impedance at port 1 ZI1, and this is the image impedance at port 2. So we need to calculate the port for image impedance at the port 1 actually. So basically you need to calculate the first. It is ZI1 only you need to calculate. ZI2 is that is not asked in this problem. ZI2, yeah. Mhm. Yeah. Equation of y11 you can calculate from this equivalent. So you can write as a you can calculate this impedance, right? So this will be equals to this will be equals to j times omega. So this impedance will be j times omega L by 2 uh, plus j omega c plus 1 by j omega L by 2. So this is the impedance. 1 by 1 by this you can this is the impedance of this equivalent network. 1 by this you can calculate the y11 if you take inverse. Is that clear? Hmm. L by 2, yeah. This is 2, this is 2 na? Right, this is L by 2 only na? Right. Is that clear? Yeah. ah, this is which one? So no, Z in this is the equivalent network of. So basically Z11 is Y11, yeah. So you like I am just like once you short circuited, whatever the admittance is that network, it's the Y11, right? So you can calculate this admittance of like, and then this will become this equivalent network actually. So this equivalent network, if you calculate admittance of this network, then basically that is your Y11, right? I think it will be simple only. It's not that difficult. J will get cancelled. J will omega will also will become common. So when you take the ratio, I think almost all the term will get cancelled. Y11. So basically, Y parameters are like see Y11 as we have drive in this class. This is equals to I1 by V1 given that V2 is short circuit, right? Right. So that basically in this two port network, this is port 1 and this is port 2. So basically to calculate Y11, you need to short circuit this port 2. So then basically this inductance and this capacitance will become in parallel and in series with this inductance. So basically you need to calculate equivalent admittance of this network, right? To calculate Y1. Is that clear? Yeah, you can like anyway admittance like either way you can calculate. Yeah, so I you can calculate either way. You can calculate first the impedance. You can calculate the equivalent impedance of this network and take the inverse. Then you can calculate the admittance, or you can just directly add the admittance and then like you calculate in terms of admittance, then that is also fine. Like either way is fine. In the if you use admittance, then you don't need to invert it, and if you are using impedances, and that you like at the end you need to invert it actually. Hmm. Huh. You can yeah, because that is simple only, because like this open circuit you did na for the port 2, then this second will become neglected actually. So you can you can calculate either way in this also, but like the because these are in series, that calculating the impedance is simpler, and we want Z11 impedance only. Where no, this I have written this I have written impedance. You need to write admittance here. So this is one, yeah, 1 by L by T. Yeah, 2 upon j omega L. Similarly, here also, this will be j omega C. 1 by, uh, uh, no, but then actually, in the series, you can't add the admittance. You can add the admittance only in parallel. So you need to take invert combination actually. Once you added these admittance, then you need to calculate equivalent of series admittance. Let's say that series admittance you can calculate just by this. So this is, let's say, y1, this is y2. Then series admittance is y is equals to y1 by 2 by y1 plus y2. In the series, admittance does not add up actually, right? So then basically, yeah. So then and also you can calculate this propagation constant similar to the your impedance line. So this propagation constant is basically like the ratio of this V1, let's say voltage at this port, V2 is this port. So this E of minus gamma is equals to V2 by V1, which we you calculate as your like you can calculate in terms of d by a times square root of ad minus square root of bc, and ad if you can take common, then basically your this will become d times 1 minus square root of bc by ad, and basically that you can equate, so basically you can calculate the abcd parameters, and this bc by ad, uh, bc by ad is no bc, no, it's not there. So you need to calculate the abcd parameters for this network. You need to calculate the abcd parameters. Once you find the abcd parameters, then basically you just plug in the abcd parameters, and you just invert this, take the anti-log of this, and you will find the propagation constant. Yeah, it's a bit difficult like that. Hmm. No. First, yeah, image impedance, like, hmm, hmm. No, like ABCD parameters is basically, so it is like that. Basically, it's like V2 by like V2 by I2 is equals to because like this image impedance is like if you can calculate like this, so the like this you need to calculate, so this the propagation constant is given by this. You can drive in terms of y or z parameter also. So if you can convert all this abcd parameter into z parameter, then that will be the equation, and you can manage with z or y impedance only. uh, uh, Yeah, it will be better to calculate with the ABCD parameter actually. Yeah, ABCD. ABCD also you can calculate. So once you calculate the ABCD, I don't know, that will be easier, or like whoever, whichever method is easier, especially this T kind of network. If ABCD is easier, then that is way better. Final answer you will get same. Hmm. Difficult. Oh, is it? Should I calculate? Image impedance is required, so like this like the image filters are there actually. So this like this image impedance is required if you want to design this all the image filters, and those kind of like different kind of methods are there to realize the filter. So basically it's a filter realization method only actually. This is image impedance method, nothing else. Yeah, actually, I think nowadays it's not used much, but I think it's just covered in the class. So, uh, I think I don't have. Uh, uh, hmm. Okay. Yeah, I will let you know in the next class, like why the exactly image impedance. Like currently, I don't have answer. Maybe I will just let just look at and then. Okay. Yeah. Yeah, yeah, this is, yeah. So I'll just let you know in the next class. I will note down. Yeah, like that. Why? Hmm. Okay, so this you try calculating. If you don't find, then like just tell me. Just I will also calculate if I can share the detailed solution. Yeah, but it will be complicated only. Okay, so so uh, uh, So, so the correct option we need to choose. So, let me just write the impedance formula. So, we have the this input impedance formula is this one. So, input Z input impedance is basically Z naught ZL plus J times Z naught 10 of beta L divided by uh, Z naught plus J times ZL 10 of beta. So this is it. So let's say, for example, series inductor can be realized by the short circuited lambda 8 section line having characteristic impedance of Z naught. So let's say short circuited line means ZL equals to 0. Then basically if you put ZL equals to 0, then it will become Z naught times J times Z naught 10 beta L divided by Z naught, and it will become J times Z naught 10 beta L, and you are using lambda by 8 line, J times Z naught 10 of beta is 2 pi by lambda times lambda by 8, then this will become 4, this will become 10 pi by 4 is 1, it will become J times Z naught, right? So this you see like this will behave like a series inductor, right? So this is the correct option. If you use short circuited lambda wide 8 line, then you can design the series inductor. Series inductor can be designed by a short circuited lambda by 4 transmission line with the character. If you use lambda by 4, then basically it will become the Z in will become infinite actually, because 10 pi by 2 is infinite. So basically this is not inductor, it will behave like open circuit. So this is correct. Shunt capacitor can be realized by open circuited Z lambda by 8 transmission line. So let's say open circuited line. So ZL will be infinite. So this term we can neglect, and this term also we can neglect. So for the ZL, uh, for ZL infinite case, this term we can neglect, this term we can neglect. So this will become Z naught times ZL divided by uh, uh, Z, J times ZL 10 of beta L, and ZL will get cancelled, so this will become Z naught divided by J times 10 of beta L, and shunt capacitor. So basically so you see like if you take lambda by 8, then this 10 beta L will become equals to 1, then this capacitance has become 1 by J times 1 by Z naught. So you see like this has become like this has become like a capacitor actually. So with like if you take this characteristic impedance as 1 by Z times 1 by this, then basically you can realize the shunt capacitor actually. So the correct answer is this one also, like the first and threes are correct answer. So the fourth one is correct answer. So is that clear? I think this was fairly simple. So yeah. Okay, so am I audible? Okay, fine. Okay, yeah. So I think that this was the last problem for today. You have any doubt further? If you can ask, or otherwise we can end this session. It's basically like if you want to, let's say you want to design a shunt topology or series topology. For shunt topology, actually, a short circuited line is better. For series topology, open circuited line is better. So, like some application you will require, you need to, you can't use shunt. Like for example, there are some devices which you can't shunt. Let's say transmission line, you can't shunt. You can only connect it cascade. Let's say, then basically you can't have like let's say coaxial line. That is a transmission line, but you can't. Let's say you have fabricated coaxial cable. You want to design some impedance or some length of impedance. You want to tune. Now like coaxial cable you can't like connect in parallel or something, you can use in like in cascade only. So it's better you use in like if you want to use any transmission line, you use in cascade and series actually. So those kind of like which kind of mechanism you can tolerate, or shunt line, basically like waveguide you can create the shunt line, but like suppose you want to impedance match a waveguide to a resonator, let's say antenna. So antenna will resonate. Now if you are making, let's say, series line open circuited line with the waveguide, so what will happen, because it is open circuited line, there will be a power loss to the air actually. So that's why in this case maybe better is you to use like a shorted line so that you don't have power reflected at the end of the waveguide. So I hope you this answer actually. Yeah. So basically, like you want to, let's say you want to match a waveguide which is feeding to an antenna, radiating antenna. Now, if you want to match a impedance, you have two options. You can either use open circuited line and short circuited line. But if you use open circuited line here, then there will be, if you use open circuited line, then there will be a radiation loss because of that. So to avoid that, you use a short circuited line at the end. At the at the uh, radiation loss you will have. Mhm. Yeah, so basically that's only you need this impedance transformer and those lines. So shunt and series kind of topology. So then basically for those cases you need like different kind of combination. And suppose you want to match to a coaxial line, so you can't connect anything in shunt. So then only option is series line you connect actually. Coaxial cable, yeah. Yeah. Yeah, short circuited and series series you can use open circuited. Yeah. So in series open circuited is better because like you need to let's say this is a coaxial cable. Now you want to match to this antenna. If you use short circuited, then it's not possible. So you if you want to connect this line to this, then basically some length L you use open circuited line actually, right? Because then they because then there will not be, first you can't connect any shunt with the coaxial cable, that won't work, right? If you connect in the series, all the end will be covered only, there will be no open radiation loss actually, right? Hmm. Yes, open circuited, and this is in series only because this is connecting in between, right? Yeah. And I use in my lab. Yeah. So I Yeah, so I use in like this triple stub tuner I use. So basically my things are this. So I have a work with the like with this spin cavity system. So I have a resonator, microwave resonator, that is cavity resonator. So basically that so to excite that resonator, basically I use a coupling loop actually. So that coupling loop, because that is a shorted coupling loop, so its input impedance will not be matched. And I have like the coaxial line which is 50 ohm line, right? So to match this something, so I use a series stub tuner, so which is a stub tuner, and in between these three shorted stubs are there. So because this is a waveguide, so in that basically shorted stub can be used, shorted parallel stub can be used. So that I connect this whole assembly stub tuner in series with the coaxial line, but in within this there are parallelly shorted stubs are there. So for that actually it's used actually maybe. Hmm. Coaxial cable. Yeah. So it's like those are short circuited because those are connected in parallel. Na? If you are connecting it open circuited, then there will be radiation loss. These are open circuited. So these are short circuit. These are short circuited because see like this, because these are connected in addition to the main transmission line. So main transmission line is this. That is connected in series. So, ah, ah, that is the main transmission line that is connected in series because there is no other options you can have. Yeah. Huh. Huh. So to this main, these are the shorted parallel stop. Hmm. So basically, like you can, so now if you use this only this transmission line, you can't tune the resonance. So to have a tunability, you connect a movable stuff that you can match to. Yeah, so that basically any at any frequency, any impedance you can match. Yeah, you don't need to use different stuff. You just need to move around actually. So like that. Yeah. Yeah, based on yeah, specific frequency will get matched. Yeah. Yeah, I use this like triple step tuner like this. I'll tell you. I have used this. Mori. Uh, so it's like looks like this. So this you image is there, right? So this is the line, and this is the main line, which the two SMA ports, and these are the other three the coaxial like three shorted stubs are there in addition to. No, no, you can move like those are like length. You can move up and down those knobs actually. So length and yeah, so that stub position is changing means the you are changing the length of the shorted transmission line basically. Huh. Yeah. 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 Okay. So this was yeah. This was okay. Fine. I think you have any other doubt? Yeah. Okay. Hmm. Huh. The only like application is impedance matching is. So in even if your phone you see the microstrip antennas, those are also like they design this microstrip impedance matching network they design in that. But because that operate at a single fixed frequency, like whatever your GSM or whatever band your phone or any device support, so that basically once you design it, then it will remain. You don't need any tunability or those things. But in our case, actually, like because our resonance frequency sometimes drift depending on like how far you are away from the cavity and those things. So basically, like you need some tunability, a tunable tuner you, not the fixed impedance matching. But in the all the commercial device, mostly they use fixed impedance matching actually. So once you design for a particular band, it will match for that band and it will work. Okay, fine. Thank you so much for listening. We will meet on same slot next week. Thank you so much. Bye. Have a good, great time.